All right, welcome to IA201. Today we're going to do a chapter review of Chapter 6. Chapter 6 is a chapter on mechanical input control devices. So these are the things that we've already talked about a lot in the book, shown in drawings, learned the symbols of already, but now we're going to do a deep dive on these devices and we're going to talk about how they specifically work. However, let me just tell you straight, there are so many input devices out there that we're only going to focus on the ones that are most common, and we're really not going to do a super deep dive on any of them. But we are going to learn some key terms and some very important things as a maintenance tech that you get used to doing for any kind of input to any kind of control system. Also, let me tell you that these devices are becoming less and less as the primary method of controlling machines. Many machines are starting to use something called an HMI, which stands for Human Machine Interface, which is a small screen that can be programmed with graphics, a little touch screen that lets you control your machine from a programmable touchscreen rather than traditional push buttons. But there are still other devices out there that will always remain out there, like primary on-off switches, like pressure switches, and so forth. So we're going to focus on all of them and recognize that some of them are slowly falling out of favor. So Section 6.1, industrial push buttons. That's one that is slowly falling out of favor. And we're going to talk about them a little bit. We're going to wire them up and use them in our labs, and that's great. But recognize that over time, there are fewer and fewer of them out there. Now, in your lifetime, you're probably going to get plenty of them in your initial careers for the next 10 years. It's probably going to take 10 years for them to be replaced by other devices out there. Key terms: legend plates. These are the little special plates that can be specially made that when you cut the hole in your enclosure to install a push button, you got to get this legend plate to stick on that hole that creates the label to tell you what that switch or push button does, right? You can buy them blank. You can buy them with standard terminology like on, off, reset, run. They are available in a lot of different colors and standard styles. They're expensive as heck to get custom made. So there's a lot of them out there, and they're very, very important for your operators to have a label, a legend plate that is on their push button. If they don't know what that push button does, you might be in trouble. The diagram here is actually very important on the top of page 142. In this book, we see what the normal configuration is for a standard push button device. And you can see you got a lot of parts that all screw together. This point right here is where usually you've got it piercing an enclosure wall. You've got an enclosure, a steel enclosure, right? And so all these parts go in front of that enclosure, and then all these parts get screwed in behind that enclosure. Most push buttons have removable operators, that little pushy part. You can change out the different colors, styles, depending on how you buy it. Most push buttons have changeable light bulbs. You can go from 120 volts to 24 volts or whatever. And a lot of them also have changeable contact blocks. So I can screw in a normally open contact or a normally closed contact, depending on how I want to use that device. The ones we get from Automation Direct can actually have two different contact blocks screwed in the back. So I could have two normally open contacts or two normally closed. So I can actually buy these separately in different configurations, or I can build them myself in different configurations. There's a lot of different kind of methodologies there. The book talks about operators. Operators are the range of things that the operator actually touches to change some sort of contacts when I run that particular push button or switch or whatever. So it shows different kind of operators in the book. And we learn about mushroom switches, like E-stops are generally jumbo mushroom button operators. I don't know if jumbo is a standard term. Usually it's specific to different vendors that sell different kind of operators. And there's more than just these options. They show you 3 basic options for operators: the flush, the extended, and the jumbo. There are a lot more than that out there, depending on the manufacturer. The book talks about contact blocks. Really important to understand that, how you can screw different kind of contact blocks on the back of many push buttons. Older industrial push buttons don't have screw-on contact blocks. They're built into the push button. Often you have a pair of normally open contacts or normally closed contacts built into these push buttons, and you can see the symbols that you would use for the different styles.
We can't see what you're circling. The camera isn't centered.
Thank you. All right, let's rearrange that. So I'm on page 143, and I'm just showing you that there are a variety of contact blocks that are available, and depending on the push button and depending on the manufacturer, you can select a variety of styles. These tend to be the older industrial styles that have this approach where the contacts are built into the push button. The newer ones often have replaceable blocks, like the ones you get from Automation Direct have replaceable contact blocks. And let me just grab one for illustration. This is an Automation Direct push button. And the push button itself is, you can press it, and when you press the push button, all that happens is this plastic piece pops out from the bottom. All right. Actually turn it into a push button that has contacts. I had to screw one of these contacts in here. And this particular push button is designed to have 2 sets of contacts screwed into it. I can screw that contact in there, and now when I push this push button, it makes contact across between these 2 terminals. I can have a green contact. In the case of this manufacturer, green means normally open. I can have a red contact as well, which would mean normally closed. So this is a classic 22 millimeter push button. The 2 standard industrial sizes are 22 millimeter, and they mention that here. That's called a miniature size, very important on page 143, and 30 millimeter. And technically it's slightly bigger than 30 millimeter. It's actually 30.5 millimeter. But the 22 millimeter is becoming the standard for most medium and small control panels. The 30 millimeter, the fatter ones, were probably the standard 20 years ago. And I guess they're slowly being replaced, especially over in Europe and other places where they build this equipment. So those are the 2 standard sizes when you buy this equipment that really have to do with the diameter of the hole that you would punch to install this. Not the diameter of the push button or anything to do with the back. It has to do with the diameter of the hole that you're going to punch to install this equipment. In the book on page 144, it goes through NEMA enclosure classifications. And if you're doing any kind of replacement of equipment, this is really important. You got to know what your NEMA enclosure classifications are. NEMA 1 is just an indoor box that it's got basically no special characteristics. NEMA 3 is an outdoor box that's designed to be, kind of keep it safe from normal rain and a little bit of wind and ice and stuff like that. It doesn't usually help you if you got heavy wind blown rain. Sometimes that can blow into these boxes and the vents. That's a pretty typical outdoor one now. NEMA 4X is another common enclosure style. They tend to be stainless steel. They're designed for wash down, hose down, so I can have blasts of water on them that'll keep everything inside there safe. And they are kind of the standard for kind of applications such as pharmaceuticals, operations, chemical operations, or food. You're going to you see NEMA 4X used everywhere. And then you've got other NEMA ratings as well. NEMA 13 is a common dust-proof one. You're going to see NEMA 12, NEMA 13. As indoor dust-proof and oil-proof. NEMA 12 is probably the most common. So NEMA 1, NEMA 4, 4X, and 12 are your more common application enclosures. So you need to know how to order these enclosures. This is a very important page, not so much from the course, but in real life. Understanding what NEMA enclosure styles you need to order for the right location is very, very important. In section 6.2, selector switches, we get into the various kind of selector switches, and they're very similar to your push buttons. You can have multiple position selector switches, and 2 position is the most common. 3 position is also common. Usually they're maintained. So they mention maintained or not maintained, but sometimes you can have a 2 position switch, which is momentary. So I rotate the switch, and when I release it, it springs back to its original position. It's kind of like a push button, but a switch instead. I don't know why you would want to switch for that, though some operators prefer that. Mostly use a push button for momentary and a selector switch for maintained. You have to be careful when you buy these selector switches that you make sure that they're maintained if you buy a 2 position selector switch. And they go through the standard examples, very important. Now let's go through a concept that they use in the book called truth tables. A truth table is simply a way of documenting in a simple table what the possible conditions are for contacts, depending on what the condition is of the switch. If you have a 2 position selector switch, it's pretty much straightforward, right? Your contacts are either going to be open or closed, depending on the position. If you get to 3 positions or more, then you start to really want to know what contacts are open and closed, depending on what the condition is. In both of these selector switches, I only have 2 sets of contacts, A and B contacts. And so it's important to know how I'm going to use that switch to know which contacts are closed in which position. So this is a very important concept. And I think they give you a great visual diagram of it on page 146. Now, the next section, joysticks, is much less common nowadays than it was, say, 20 years ago. More and more joystick systems are electronic at this point. Joysticks, I mean, we all know what joysticks are from gaming. Our controllers have little thumb joysticks that 2 of them usually for most gaming systems that you can push up and down. Some people still use joysticks on their PCs, though. A lot of people just use the keyboard, but it allows me to have a physical device with multiple positions, and I can have it 2 position, 3, 4. These are still used a lot in hydraulics, but for the most part, they're relatively unusual. It's an interesting thing. But each position would then have a particular contact associated with it. And once again, you need a truth table to figure that all out. This is showing you an example of a 4-position joystick. Shows you that each contact in which position it closes, and then it shows you an example wiring diagram using those joystick positions to turn on different motors. Limit switches are also extremely common today. I mean, joysticks is now less common. Limit switches everywhere. You're going to see limit switches everywhere, and they are moving parts. They break a lot, so it's easy to bump into them with a forklift or something like that. They, anytime a machine jams, you potentially put a limit switch at risk. So these are something you're going to end up having to replace if you're in a maintenance field. Very common thing. A limit switch is simply a switch that when it rotates or presses in or has some sort of operator on it that moves, it closes or opens a contact. It can be set up normally open or normally closed. And they could be set up normally open, normally closed, or I can have a limit switch which is held closed when it's in a normal condition. It's a normally open contact, but it's held closed when it's in normal position. And each one of these has its own little diagram. So it's very important to understand this concept of held closed or held open. That means that mechanically, the way that machine is configured, it's something is pressing up to it in normal condition. The book talks a little bit about limit switch activators, but the truth is there are literally hundreds of different kinds of limit switch activators. The typical one has a little lever with a roller on the end. That means you can have a variety of different, doors or carts or something that bumps against the lever and causes it to rotate. And that's a very typical one, but you see literally hundreds of different kinds of actuators out there. They show you a little picture on the bottom of page 150 with just a handful. You can go to a variety of limit switch manufacturers and see the hundreds and hundreds of possibilities, combinations of things in the limit switch. The book talks a little bit about limit switch installation, gives you a couple clues. Not a whole lot of genius there to figure that out. It's really more trial and error once you get on the field. You have to make sure you test it thoroughly in both positions, and you got to make sure that it can't be damaged if something over travels, or make sure it's covered and protected from vehicle traffic or humans working nearby. They give you a few examples of limit switches in the book that are good, so read through those examples. Foot switches are still pretty popular. They tend to be used when an operator needs to use his hands and his feet to control an operation. They are becoming a little less common because of OSHA rules. If an operator can stick his hands into an operation because he's operating a press or some device by his foot, it's actually kind of dangerous for him. You don't want to have his hands in operation. So many machines that used to be run by a foot switch now are run by like 2 push buttons where you have to put your hands into little enclosures before you can fire up the device. But many devices still have foot switches out there. It's basically a push button for your foot. Pressure switches are getting into measurement systems. You're no longer in operator kind of switches. Now you're measuring the world, and they look at the pressure differential between something that you're measuring, like a chamber, a vacuum chamber or a pressure chamber, and the outside temperature. That's a very common thing. Obviously, everybody's got a pressure switch built into your compressor. When the compressor reaches a certain pressure, it builds up pressure behind a little diaphragm here. That diaphragm pushes on a switch. Depending on the tension of that spring, it will determine what the maximum pressure allowed is. And usually you can use adjustments to adjust the pressure on that spring. And this is the symbol for a pressure switch or a vacuum switch. They're used very commonly in compressor applications, so they're useful. Talks about different applications for pressure switches, and it talks about different kind of, well, actually, at this point, some key concepts get in here. We talked about methodologies, but once we get into this concept of deadband, that's an important key concept for many devices. The idea that you've got a pressure switch where you set the pressure at the higher level, like let's say you've got a 100 psi compressor, right? So your system, when it kicks on, will pump up to the set pressure, 100 psi. But once you start using, like you run your air gun out of that compressor, you start using some of that pressure up, it's not going to kick on instantaneously as soon as you drop below 100. It's designed to kick on once it drops below the dead band. As soon as it drops below the dead band, it'll kick on again. Now, why is that? It's both by design and by the accident of construction of these pressure switches. By design, you don't want your compressor constantly kicking on and off. Compressors and many motors are designed to so many starts per hour. This is a very important concept, so many starts per hour. And if you start a motor too much, it will burn it out, especially a single phase motor using a capacitor. If you restart that motor too many times in an hour, that capacitor begins to heat up and eventually will explode and need to be replaced. Okay, so we talked about the concept of deadband, and that is when you're pumping up that compressor, your pressure gets higher and higher, it's going to reach your target pressure setting on the switch, and then it's going to kick off. And then as you use the air out of that compressor, it's going to drop below, but it's not going to kick on right away. It's going to drop below to a particular reset pressure point, and the difference between the setting pressure and the reset pressure, that change is a dead band. And it's usually what, 2 to 5 psi for a lot of compressors. So that way your compressor isn't constantly turning on and off, right? It waits until it drops below the dead band before kicking on again, and then it runs for a little while, and then it kicks off again. And the setting here has to be based on how much volume of air you're using, and the quality of the compressor you pick will partially be due to how much air you're using and how often. So you need to check your dead band very carefully. And the book does a good job of explaining the dead band and what that is. But that's a very important concept because we use that in a lot of different kind of input devices to a variety of control equipment. And the book gives you several examples of different kinds of pressure switches and so forth. So I'm not going to go into them because you can read them. There's nothing particularly new in there, but they're very interesting. Now we're into temperature switches. Temperature switch and pressure switch are probably the most common environmental on-off devices used in our automation world, so they're very, very important. Temperature is simply the same as pressure. Temperature switches are used in so many devices in our household, in the industrial world. We've got temperature switches built into our dryers so that if our dryer doesn't reach a maximum temperature properly, or does reach an over temperature, it'll turn off the dryer and turn on alarms and that sort of things. These are relatively inexpensive devices, or they can be relatively inexpensive devices, and they're used all over the place. They're usually purchased for a particular temperature, the cheap ones. So they don't really have settings. The cheap ones don't really have settings. They are designed to automatically open or close, if you buy them normally closed, when a temperature is reached. And we give you various applications here. In this case, we've got a heating system with a very simple temperature switch. All right, in this case, we show a heating system being controlled by a contactor. That C means a contactor. And that contactor is being controlled by a temperature switch, which is a normally closed. I show it as a normally closed switch. And basically, temperature switch is just a switch with a line going down and then this little square squiggle. Square squiggle is a temperature switch. All right, when the temperature reaches a certain point, it opens. When it closes, that means the temperature is cooled to a certain point. You can buy these normally open or normally closed. Same thing with flow switches. Flow have to be in line to a fluid, air or liquid of some sort, and they will determine whether a certain flow rate has been reached or not reached. In our house, many of us have propane heating system. If you have a propane heating system, there are flow switches set up to make sure you have air flowing through the exhaust. So as you warm up your hot water or turn on the heat for your house, that the exhaust coming from your heating systems is being ejected outside. So there's flow switches there. So we talk about different flow systems in different examples there. A flow switch looks like a little upside down flag, right? Level switches are often the same thing as pressure switches, but there also could be limit switches. So you might have a little float inside of a chamber, and then when the liquid gets up to that float, it rocks upward like a limit switch and causes a contact closure. So these are very common devices that are very, very similar to limit switches or pressure switches. I can have a pressure switch level indicator that can be set based on the height of the liquid in the chamber. When it reaches a certain height, that pressure switch turns on. And there's a few different types they mention here. The mechanical, like the limit switches, the probes, where you basically have two little wires going on in there, and when there's conductivity between the two wires, we know it's reached that level. Capacitive, and it goes through all different kinds of level switches. Chapter section 6-10, preventing problems when installing control devices. This is just a series of sort of general good advice. Protecting switch contacts, because the contacts, these little metallic contacts, which can be silver or gold if you have a really good quality one, or copper, they will have problems with oxidation, or if you get any goop in there, that'll jam them up for sure. So they just talk about general strategies to protect them electrically as well as physically. Protecting the pressure switches, there's different techniques to keep them from being blown out. Talks about installing flow switches in places where you're not going to have turbulence, because flow can't really be measured if you put it right near a pipe corner. So you really need to have a certain rule of thumb for setting up where you're going to do a flow switch, which in this case is 3 pipe diameters from any junction or disturbance, and some basic testing. So that's pretty much it for my book review.